In this video, we're going to look at implementing a linear regression model to predict disease progression. Let's go right in. So I'm back in my chapter 4 checkpoint. And so in this video, we first want to go to in32, where from scikit-learn.linear model, we're importing linear regression, which is scikit-learn's implementation of a linear regression model. The reason why we want to use the scikit-learn model instead of the one that we've implemented in the last video is because scikit-learn is an open source project that has leveraged many people's time and expertise to perfect the implementation of linear regression. While linear regression is not the most complicated model in the world, doesn't mean that it's very easy for us to implement correctly, and it's very difficult to build a suitable data science or machine learning project if you're also second guessing whether the implementations of your algorithms is correct and not just what's happening with your data. So in conclusion, in in32 we import from linear model the linear regression model. In in33 we're again importing a different function from the scikit-learn package sklearn.model_selection. This particular function is called train test split. So let me explain a little bit about what train test split is about. If you have a data set, and let's say this data set has 1,000 data points, if you simply take this 1,000 data points to train your machine learning model, you don't have remaining data points left that the model hasn't seen. Therefore, it's very difficult and almost impossible for you to test how your machine learning model will react and perform when it is exposed to data that it hasn't seen. And if you think about it, once your machine learning model is done and you deploy it in the real world, that's exactly what happens, right? Your model sees and performs against real world data that it hasn't seen before. This phenomenon is called generalization. And the generalization power of a particular machine learning model is a key topic and performance indicator in any data science project. So how do we solve this problem? Enter train test split. Like what it says in the label, we're splitting the datasets into a training set, which is used to train the machine learning model, and a test set, which is used to test the model's performance on seeing unseen data. In in34, we're running the train test split function in both inputs and the outputs to pair them up to create a coherent supervised learning dataset for our linear regression model. We specify that the test size is 0.33, i.e. 33%, and the random state is 42. So why is there the random state there? So the random state allows us to very clearly reproduce the data because train test split randomizes your data first and then takes out a proportion of the data into the test sets. In this case, the proportion is 33%. The random state parameter allows you to replicate this randomization element in the train test split function so that it's easier for other people like yourself to replicate what I've done here in the Jupyter notebook. Train test split returns 4 variables in a tuple. There's xtrain, which is the input of the training sets, xtest, which is the input of the testing sets, ytrain, which is the output of the training sets, ytest, which is the output of the testing sets. In in79, from sklearn.preprocessing, I'm importing some preprocessing functions. The preprocessing functions I'm using is polynomial features, standard scalar, and to combine these preprocessing steps with the main linear regression model, I'm using sklearn.pipeline, import make pipeline to make a pipeline of transforms and estimators. In the 4th line of in79, I'm creating a new pipeline and assigning this pipeline to the variable pipe. This pipeline consists of one step, And this step is the linear regression model that we're so familiar with. After that, we take this pipeline and we fit it with the X-train and the Y-train data. Let's look at how this pipeline is performing. In in80, we score the pipeline on the training data. We can see that this pipeline scores 50.1% on the pipeline. Let's see how it performs in unseen data. If we look at the scoring on a unseen data X test paired with Y test, we can see that the output gives us 51%, which is very similar to the training performance. Let's look at what else we can do. In regression, one of the variations of linear regression is to perform ridge regression. This tactic allows us to minimize weights of different features on the model, and we make sure that the smaller the weights is better, and there's a higher penalty on larger weights in the model. So we make a new pipeline consisting of the standard scalar, polynomial features of degree 3, and ridge regression. Again, we train this on the training data by calling pipe.fit xtrain, ytrain. And let's inspect the coefficients of the pipeline. In in75, we call pipe.steps 2, which is the last step of the pipeline, 1, which is the model object itself, and we call the coefficients property of this model. We can see that the coefficients are very well behaved. In in76, we look at the maximum and the minimum of these coefficients, and we look at the standard deviation. We can see that the coefficients max out at 65, min out at minus 45.5, and has a standard deviation of 14.5. So none too shabby. If we score this pipeline, we can see that it scores very, very well, 83% in fact, in the training data, but the testing data is abysmal, so it's negative 1.03, which basically means it's worse than random guessing. So let's try a different strategy. In in70, we're importing from the linear model the variation lasso. Lasso minimizes the number of non-zero weights. In in70, we create a new pipeline consisting of standard scalar, polynomial features of the degree 3, and lasso at the back. In in71, we look at the training score, which is 64%, the testing score, which is 47%, and if we look at the coefficients, we can see that a lot of the coefficients are 0, which has achieved the regularization objective of us using lasso. And that's all there is to it. The next section, we're going to look at classifying wine types